Hello, everybody. Welcome to Complex Analysis with Applications. In this lesson, we will go over basic properties of complex numbers. To begin with, we start with the definition of complex numbers. So what is a complex number? A complex number is a number given in the form of z equals x plus iy, where x, y, both of these numbers are coming from the collection of real numbers. And the purpose of this special symbol, I, is to stand for, roughly speaking, to stand for the square root of -1. But we have to be careful when we write it in this way. So more precisely, it is I is the principal root of -1. And we will see this idea more precisely later. But now, if you consider a complex number given by x plus iy, we can immediately connect it with some geometric representation. We can talk about the complex plane. On the complex plane, you can recognize on the vertical axis, we indicate the real axis, and the horizontal axis is the real axis, and the vertical axis is the imaginary axis. So in other words, if you measure x units in this direction, and if you measure y units in this direction, this number that corresponds to this point that corresponds to the coordinates x and y is indicated by x plus iy. In other words, we always multiply whatever this number, which is called the imaginary part of the complex number. So when you call this is the imaginary part. So when you talk about the imaginary part, that does not include I, it is just what's multiplied by I. And then this component, x, is called the real part of the complex number. So every complex number has two pieces, a real part and an imaginary part. But one can see all numbers that we have learned up to this point as real numbers are also complex numbers. Because if you consider any real number, like let's say x is none other than x plus I times 0. Of course, this gets muted because it is multiplied by 0. So in other words, if you look at the real axis here, that is none other than the same real number line that we've been considering up to this point. So now, based on this consideration, now starting from this definition, what can we say about complex numbers? What are the properties? Now we need to analyze many properties behind complex numbers. So let's begin with some technical information, some terminology. So starting step, let's get familiar with the terminology or the language. Language of complex numbers. Now we always say, sometimes we will use the lowercase symbol, also z, in this form, equals x plus iy, right? When I indicate a number like this, starting step, as I mentioned, now the real part of number z is indicated by this symbol. Real part of z, and that is none other than the x coordinate. And similar to that, imaginary part is none other than im, im, and then z within parentheses. So in that way, you can extract exactly the real component and imaginary component whenever you need to talk about them precisely. And then, by any chance, if a complex number happens to be, if the real part of a complex number happen to be zero, in other words, if this part gets muted, that lies on the vertical axis, and that kind of the complex number is called a purely imaginary complex number. Pure imaginary complex number. So it has only the imaginary component. Now, when do we say two complex numbers, right? Z1 equals A1 plus IB1 and Z2 equals A2 plus IB2. Now, when do we say Z1 equals Z2, right? So when do we say Z1 equals Z2? We would say Z1 equals Z2 if and only if this symbol denotes if and only if. So whatever the condition I'm about to write here will be necessary and sufficient for this condition, right? So that would be exactly the situation where A1 equals A2 and B1 equals B2. So in other words, there is a very nice uniqueness property. Two complex numbers would be the same if and only if they have the same real number and same real component, real part, and the same imaginary part. Now, this can be understood very nicely if you look at the complex plane. If you have two numbers, to have them coincided with each other, of course, you need to have the same coordinates. So now, based on this basic terminology, let's think about some other stuff that we can learn. All right. So yes. All right. So why don't we have a title for this? The complex conjugate. So if you consider a complex number Z1, or like let's call it Z, A plus IB, right? If you consider a complex number, then the conjugate of this number Z, conjugate of Z, is indicated by this symbol Z bar. Always, whatever the number that we consider, we put just a bar on top of that, Z bar, and that is none other than A minus IB. We have seen conjugates in algebra even without having this imaginary component. But now, when you consider imaginary components or complex numbers in particular, it is very convenient to understand the role of the conjugate of a given complex number. All right, so let's do this now. So we know a complex number, we know the real part, we know the imaginary part, and we know the complex conjugate. Now, let's talk about operations. Operations on complex numbers. Now, to begin with, let's talk about complex. Let's have two complex numbers. Z1 equals A1 plus IB1 and Z2 equals A2 plus IB2. Now, whenever I write two complex numbers in this form, Now this form is called the standard form. Standard form of a complex number. So keep that in mind. Uh, Here, I'm not gonna keep this writing in the middle of our arithmetic operation definitions. However, keep this in mind because there are other representations. So whenever you have this standard form of a complex number, if I represent a complex number by a standard form, by the standard form, that simply means I implicitly assume the fact that A1, A2, B1, B2, all of these, like these are given in standard form. So these numbers are sitting in the real number. So sometimes I may not talk about this condition explicitly, but it is always the fact whenever I write down the standard form of a complex number. So now when you consider two complex numbers of this form. Now, how do we define this new operation? This is a new operation because it's acting on complex numbers. So what would that be? That is none other than adding these two complex numbers, but it is very intuitive at the same time. If you add two complex numbers, what you should expect is the addition of real parts together and then the addition of imaginary components separately multiplied by I. And then if you consider z1 minus z2, it is obvious a1 minus a2 plus I times b1 minus b2. And then at the same time, if I include one more real number in this, let me include one more number in this list. I will call it like lambda, one more real number. If I consider any real number, and if I multiply one of these numbers, like let's say lambda times z1. So I'm going to multiply z1 by that real number. This is a real number. So if I do that, that is not going to do anything surprising. That's going to be lambda times a1 and then I lambda times b1. So in other words, it will just multiply the real part and the imaginary part separately. And then what would be the product of two complex numbers? The product of two complex numbers is going to be, basically, it is just the most intuitive way of thinking about this. I b1 a2 plus I b2. Now think about this. Think about it just like foiling. If you foil this, what would you expect? Now, in fact, this is not just an operation that we are performing. It is in fact a definition. The product of two complex numbers itself is a definition and it is not a derivation. However, it's really important to understand in mathematics when we construct new definitions, when we construct new tools, it should be consistent with what we have seen already and it should be intuitive in terms of what we have already established. So that's exactly why I would just encourage this intuition right at the beginning. Think about foiling this. So if you multiply this just by A and then by B, right? When you multiply by the first part and the second part, what you're going to get is A1, A2 plus IB1, A2. So IB1, A2 and then IB B2 A1, right? It could be the other order. It doesn't really matter. It's going to be the same component. So B2 A1 And then the last component will be I times B1 times B2. So I square B1, B2. When you consider I square, the purpose of I square itself is to represent -1. So it is the principal root of -1. Simply, if you square it, you're going to end up getting -1. It is one of the numbers that would give you this, one of the numbers that would satisfy the equation x square equals -1. So in simple words, whenever you square whatever that number, you should get -1. So that is what we are going to have here. So you will get I square B1, B2 with a plus sign, but when you make I square, when you convert it to -1, it turns out to be this. So now this is in fact a definition, and this definition is highly important. I mean, you may feel this is rather elementary uh, observation. That is natural. But the most unnatural part about the construction, or like what holds the entire domain of complex analysis or complex numbers, is this product, the product of two complex numbers. Because you can again see two-dimensional space. You have seen that before. R and R. There also you have ordered pairs. You can indicate X and Y, right? X and Y. So in that way, you can identify this point X, Y. And then you can analyze this as a vector space. So if you consider this plane, the ordered pairs, the space of ordered pairs, or in other words, the space of two-dimensional real numbers, two-dimensional Euclidean space, sometimes as we call, is this structure same as the complex plane? Is this, roughly speaking, what I'm asking is this the same as the complex numbers? The answer is no. These two are not going to be the same structures, because when you consider complex numbers have this amazing product rule, or the product property, or the product between two complex numbers. So that's exactly what will stand out as a separation property between R2, two-dimensional Euclidean space, and complex plane. All right. So now we can see more information about this rich structure of complex numbers. Like when we work with more, you will see more. Then let's talk about division of complex numbers. Now, yes, division of Z1, we considered Z1. All right, so let me follow the same terminology, the same notation. Z1 divided by Z2. Let's be clear with the notation. Z1 over Z2, where A1 plus IB1 is Z1 and A2 plus IB2 is Z2. Now, how can you define division of two complex numbers? Now, before talking about division of two complex numbers, let's talk about, roughly speaking, let's talk about something that we can fit in here. That's exactly why I left some space. If you consider the conjugate of a complex number, let's say, first of all, I'm going to talk about this 1 over Z2. So 1 over Z2, if I consider that number, it's none other than A1 plus A2 plus IB2. Now, if I need to take uh, any complex number, if I need to put a complex number in the denominator, there is a very easy way of simplifying the complex property of that. I mean, the complexness. Roughly speaking, if we just try to handle that complexity, how can you simplify it? This is an easy way. And this should have been listed as one of the properties where once we introduced the complex conjugate. But look at this. We know whenever we need to simplify some complicated terms, the conjugate is going to help. So I'm going to multiply this number by its conjugate. The conjugate of this number is exactly what you see here. Now, if I multiply, what do I get? In the denominator, when I combine these two, what I'm going to get is a2 square minus I square b2 square. Let me write it. A2 square minus I square b2 square. That is none other than just simple algebra, right? The product between two conjugates. And at the top, you have just 1 times this complex number, which we know nothing other than a1 minus a2 minus ib2. So now if you look at the denominator, you can clearly see this is none other than -1 in the position of I square. That's going to be that's going to change the negative sign in front. So in other words, it's just a2 square plus b2 square. And then at the top, you have a2 minus ib2. If you look at this number carefully, can you see the denominator is just a real number? It's the square of the real part plus the square of the imaginary part. So that simply gives you the complexity or the real and imaginary components, or the active imaginary component only located at the top. So in this way, you can just play with any division by a complex number just by using the conjugate. You can make it a product. And how can we do that in this occasion? For instance, look at this, the way that we are going to do z1 over z2. That is none other than considering this one as a z1 times 1 over z2. We will consider it as a product. And we know z1 is none other than a1 plus ib1. And now, according to what we've seen already above, 1 over z2 is none other than a2 minus ib2 together with this real part, real component. So now what I can do is, by knowing that this is a real number, just to separate these issues, let me just write it individually. And then what we have essentially is a1 plus ib1, a2 minus ib2. Now this is none other than just the product form that we've learned before. Based on that, I can simply write it down. A1 square, sorry, A2 square plus B2 square. And in this component, I can just have A1, A2 minus B1, B2. In fact, it would be minus, minus, that would make it plus. And then we will have the cross terms. That would be I times B1 A2 minus A1 B2. Let's use brackets to build this. So now in this way, we can have the product of we can have the product and we can have the division of two complex numbers. Now let's look at a couple of examples. Let's play with a few examples specifically related to numbers. Numbers and simplifications, right? So first of all, let's look at -1 plus 2i plus 3 plus 7i. If I need to find the summation, it is none other than just add, right? The real numbers, the real parts, and the imaginary components. And then if you need to multiply, it's easy now. Just multiply the real components, and that would be -3. So -1 times 3, -3, and then 2 times 7, that's 14, and then I times I would make it -1, so -14 plus I times 6, and then -7. So 6 minus 7. Now you can simplify it. -17 minus I. So in the same way, you can consider like different types of simplifications. Let's extend that to a slightly more complicated combinations, which would help work with the assignments as well. So what if we consider, let's call this example number 1, example number 2. Let's simplify 3 minus I, 2 plus 3I divided by 1 plus I. Now there are 3 pieces here. You need to take the product and then you need to divide it by this number. Let's not mix it up. If you want, you can do it like this too, right? You can just make it the product of 3 complex numbers right away by multiplying the bottom number by its conjugate, 1 minus I. So if you multiply at the bottom, you need to do the same thing at the top to avoid altering that term. So the starting step is this. Let me have this new term in new color, right? So this is what we need to simplify, and we additionally came up with this multiplication and division. And once you do that, you can end up getting the conjugate. When you multiply these two numbers, you can see it's going to be 1 plus 1. It's going to be just 2. And if you do not see how that simplification, how these two together will form just 2, I recommend you to do the simplification and check. So that would be 2 in the denominator. So I will write it like 1/2 at the front. And 3 minus I, 2 plus 3I, 1 minus I. Now simplify. When you simplify, of course, the rule of simplifying anything, I mean, you cannot simplify all 3 of them together. So do 2 at the beginning, and then whatever the resultant that you're going to get, multiply it by the last number. So when you do this, what do you get? First of all, 6, and then minus makes it plus 6 plus 3, And then the imaginary components right here, -2. So I times -2 and then +9 plus 9. So that is the product of the first two numbers together, yet this one is untouched. Wait until the last step to get it simplified. So now when you simplify this, you can see it's 9 minus, or it's plus 7i, then 1 minus I. Now you have the product of two complex numbers to be computed, which is again the same definition. So let's do it. 9 minus I square times 7, so plus 7, and then plus I times 7, 7i, and then minus 9i. So 7 minus 9. So it's going to be 1/2, 16 minus 2i. And if you simplify this further, you can see now multiplication by a real number is nothing other than the multiplication of the real part and the imaginary part of the same complex number. So that will result 8 minus I. So we can do simplifications of any number of complex numbers in this way. All right. Before proceeding with further examples, let's work with few properties related to the complex conjugate. Properties related to the complex conjugate. So these also are algebraic properties. However, now consider Z1, or like let's call just Z, A plus IB, and in that scenario, we know Z bar, the complex conjugate, is going to be A minus IB. Now, we have already seen a few of these properties, but for formality, let's write it. Now, if you consider Z1, or like let's say Z plus Z bar, if you add these two complex numbers, the number itself and its complex conjugate, that will result, if you look at this, if you put them together, you can see the imaginary component IB minus IB would cancel with each other, leaving just 2 times A, which happens to be a completely, it is just a real number. That is interesting. And at the same time, if one would like to analyze this a little bit and to relate it with exactly the number itself, this is none other than Z plus Z bar is 2 times the real part of Z. So one can come up with this kind of an equation. Sometimes it can be useful. The real part of Z is none other than 1/2 of the number plus its conjugate. Similarly, one can recognize a formula for imaginary part of Z, but it's slightly different. If you consider Z minus Z bar, you will end up getting the cancellation of the real part, leaving the imaginary part twice, as it was, 2 times IB. The only difference is here we have an additional term of I. But now one can see this is purely imaginary. This is pure imaginary number. And at the same time, one can say the imaginary part of z is none other than, the imaginary part is just b, so it is none other than z minus z bar divided by 2 times I. This may be used as a formula, but this this particular property is far more important as an observation. Whenever you add a complex number with its conjugate, you will end up getting a real number. And this is not the only such surprising combination. If you consider z times z bar, we have seen this computation already, z times z bar, so a plus ib, a minus ib. We know when we simplify this, it's going to be a square minus I square times b square, which turns out to be a square plus b square, which happens to be a complex number, which happens to be a real number, purely real number as well. There is no imaginary component. So that simply means whenever you multiply a complex number with its conjugate, you will end up getting a real number. And these observations will be helpful in some uh, instances. And at the same time, if you try to look at this component, if you try to give some interpretation to that, think about this. The real axis and the imaginary axis. Let me just indicate this number z, a plus ib, and we already know the coordinate. In terms of coordinates, this is going to be a and this is going to be b. And in that case, if you consider a square plus b square, it is none other than the square of this hypotenuse. So one can come up with this nice observation. If you consider the magnitude of z, that is none other than the square root of a square plus b square, which happens to be exactly the square root of z times z bar. So in complex number world, right, in complex number, uh, in the domain of complex numbers, when you deal with complex numbers, other than calling this the magnitude, sometimes we call it the modulus. So modulus of z, we indicate it by z with the absolute value sign. Of course, the purpose of the absolute value is to indicate the magnitude of the number, disregarding any potential signs involved with that. And in this case, it is not only ignoring the sign, it is ignoring some other quantities except for just the fact, just the magnitude, just the geometric sense that we need to emphasize. So now that's all about the properties of the complex conjugate, and these properties will be used frequently in our computations. Let's have another visit towards more simplifications. Example number 3. Let's consider taking some powers of a complex number, 2 plus 3i squared. Now this is none other than just multiplying the complex number by itself. It's going to be 4 minus 9 plus 6i plus 6i, so 12i, together negative 5 plus 12i. Now, it is important sometimes, like if you consider some examples like this, negative 2 plus 2i. compute, I can do the same computation repeatedly, right? This is not going to be too bad. And then again, yet again. So we can do these two together first and then multiply it with, by that. So I'm not going to do it. I'm going to leave it, do it. However, my question, the real question is this. What if we have a question where we need to take the fifth power, or even like to make it more interesting, the 10th power? Are we going to do this process 10 times? It's going to be very tedious. But that's exactly why, that's exactly where complex numbers will show one of its like real potentials in even in early stages. There are easier ways of simplifying powers of complex numbers other than just doing it algebraically and separately. So we will talk about that more in detail, especially when we get to a later section where we talk about De Moivre's theorem. We get to know an efficient way of computing higher powers of complex numbers. Now, let's do one more simplification. Example number 4. All right, so what is the imaginary part of this kind of a number? 2z plus 4z bar minus 4i, given that this z is just x plus ay. Given this is what you need to find. If you want to do this, now the first thing that you need to do is none other than just simplifying the number that's sitting inside. So when you consider 2z, it's going to be 2x plus 2y I. If you want, you can write I at the end. And then 4x, and don't forget z bar is x minus iy. So 4 times x minus 4y I minus 4i. When you consider the real components, you can see it is going to be 6x. And then when you consider the imaginary parts, you can see it has some contributions from 3 terms. Put them together. So I times 2y plus 4x and then minus 4. Now with that, we can see when you consider this complex number, the imaginary part is none other than what you see right here. The imaginary part is the real component of the second part, which is multiplied by I. So that is none other than 2y plus 4x minus 4. So in that way, you can simplify complex numbers whenever you need to retrieve real part. The imaginary part, it is just like using the same collection of tools or properties of real number, the algebraic properties of real numbers and complex numbers. So let's look at example number 5. What about the imaginary part of this number? 1 plus I times z. Again, z is none other than x plus iy. then you can simplify this. Before talking about the imaginary part, just simplify this number. It's none other than 1 plus I times x plus iy. Now when you simplify, you will see x minus y as a real part, and then x plus y as the imaginary part. So if you retrieve the imaginary part of this number, it's none other than x plus y. Let's look at solving a simple equation by using complex numbers, right? So example number 6, look at the situation where we have plus c bar equals 3 plus 4i. Now solve this equation for z. Z is of course none other than x plus iy. You can indicate it in that form. So simply, if you can solve for x and y, if you know x and y, then you know what this complex number is going to be. To start with, there are a couple of things that you can do if you do not wish to work with fractions. Just cross multiply immediately. You can do that. So you're going to have the and at this point, you can just introduce x and y into this picture, because at the end of the day, you need to come up with x and y to be able to solve. So x plus iy, and then when you multiply this number by these two, one can see it is none other than 3 plus 4i in the first part, and then plus the product of 3 plus 4i with z bar. But z bar is none other than x minus iy. Now you can solve it for the second component. So x plus iy. Now this part is none other than a regular product. So 3x minus 4 actually turns out to be plus 4y, because it's I square together with a negative sign. Right, when you multiply these two last terms, you will get negative 4y I square, but the negative sign will be simplified because of the I square, and then simplification here is going to give you I times 4x, and then the last piece is minus 3y. Now at this step, you can do it in multiple ways. You can move all of these terms to one side and simplify it further. Or you can just have them in each side and simplify each side. So it is totally up to you, the way to decide how you would proceed with the simplification, but either way, we need to simplify this. So when I simplify, I would prefer like moving all of the terms into one side. So let's say when I do that, 0 equals 3, the first component, and then I have 3x as the second component. And don't forget, I moved this term to the other side, so now it becomes negative x. And then, oh, let's have, in fact, it's not only 3, it's 3x plus 4y. and then this term appears as a negative x. I will write it, and that is all real part, the entire real part that I have for this complex number. Think about it. It's just this and this and this. You move this one to the other side. Because of that, it's negative. The rest is just the imaginary part. Don't forget, when you work with the imaginary part, you will have contribution for this one too, but it will be a negative contribution in the right side. Now let's put that together. I times 4x minus 3y, and then this terms comes to the left or comes to the right, and it will be negative y. Now each term can be simplified. The first one is 3 plus 2x plus 4y. The real part is this. The imaginary part is 4 plus 4x minus 4y. All you need to do is to solve these two equations. Now, solve which equations? Don't forget the uniqueness of complex numbers. We talked about the uniqueness right at the beginning. We know two complex numbers would be the same if they have the same real numbers, real parts and the imaginary part. So that simply means, since we equate this to 0, which is none other than 0 plus 0y, what we are going to get is 0 as a real part equals 3 plus 2x plus 4y, and for convenience, let me write down equality with 0 in the right side. Again, in the same way, the second part, the imaginary component, equated to 0, you're going to get you have two equations, and this is now simply algebra. Add these two equations, you're going to get 7 plus 6x, and these two will cancel with each other, equals 0. So x is none other than negative 7 divided by 6. And then once you have this value, you can find the value of y. Y is none other than, from equation number 1, leave 4y on left side and move all the other pieces to the other side and just simplify. So negative 3 minus 2x divided by 4, which turns out to be negative 3 minus 2 times negative 7, 6, negative 6, 7. So divided by 4. You can simplify it further, but I wouldn't worry about the simplification as far as I see the method. All right, so with this, actually, we can see there are many simplifications that we can perform related to complex numbers. Now, in the next step, we would go over some geometric properties of the complex plane so that we can visualize complex numbers better. So let's meet with more geometric and more intuitive properties of complex numbers in the next lesson, and work with more examples so that you can have more practice on these concepts that you learned. See you.